Here we have lesson 1.6, one-to-one functions. So let's start with the definition of one-to-one functions. A function y equals f of x with domain D is what we call one-to-one on the domain if and only if, here we have a biconditional statement again, for every x1 and y and x2 in D, f of x1 equals f of x2 implies that x1 equals x2. Another way to say that is that a function is one-to-one if each element of f of x of the range is mapped from one and only one element x of the domain. Okay? So it's mapped from one and only one element x of the domain. So when we're thinking about what these two statements mean, what it's essentially saying is that every single x value only goes to one y value because that's what makes it a function. But also every single y value only comes from one x value, and that's what makes it one-to-one. So here if we look at these bubbles, this diagram right here is a function and it's one-to-one because each x only has one y, and then each y only comes from one x. If I go the other direction, this direction, they only go back to one value. The second diagram here is not a function because we can see that this input of 1 has two different y values. And the third diagram here, we have this is a function, but it's not one-to-one because this input, or each input has only one output, but the output here of 4 comes from two different inputs. So therefore that one is not one-to-one. Now graphically, if we think about what that means, we know that we can do the vertical line test to test if a relation is a function. And here we have a horizontal line test to test if a function is one-to-one. So the horizontal line test will intersect a graph twice if there is one y value that comes from two different x values. And a known example of that is quadratic. So if I just draw a little sketch of a parabola here, here's a parabola. If I make a horizontal line on the parabola, I can see the horizontal line will intersect twice. So this one y value came from two different x values, x1 and x2. So this is not one-to-one. And this is just the inverse notation of f inverse of x. So how do we determine algebraically whether a function is one-to-one? What we're going to do is we're going to show that if f of a equals f of b, so two y values are the same, then they came from the same x values. Then a would have to equal b. And again, this is a determine. So determine means that we're going to need to prove it. So we need to show all of our details and all of our work. So the first thing that we're going to do is we're going to tell the reader what we're going to do. So what are we going to do? We're going to show if f of a equals f of b, then a equals b. All right. So we're going to take the if statement of this. The if statement is going to be our given. So this is going to be given, and then we're going to show that this is true or not true. All right. So our given, f of a equals f of b. And so now we're going to take our function and we're just going to plug into our function. And we're going to verify that it does or does not work. So I plug into the f function, and I can see here that when I plug into f, I get 3a plus 5 is then equal to 3b plus 5. I simplify that, and I subtract 5 on both sides. I get 3a equals 3b, so that means a equals b. So I prove that this was in fact true. So that means this function is one-to-one. But again, I'm not just going to end there. I'm going to interpret what I did. So interpreting what I did, it was shown that if f of a equals f of b, then a equals b. Therefore, f of x is one-to-one. All right, letter B. Now we're given the function here, g of x. G of x is equal to x minus 5 quantity squared. So looking at g of x, again, I'm going to first thing tell the reader what you're going to do. So what I'm going to do is I'm going to show if f of a equals f of b, then a equals b. So then the given is going to be f of a equals f of b. And here's my function, g of x. So I'm going to plug in to find g of a and g of b. And so I go ahead and I do that, g of a and g of b. Oops, and I should have put a g in there instead of an f. So this should say g of a is equal to g of b. And then I plug into my g function, so I get a minus 5 quantity squared equals b minus 5 quantity squared. And then I simplify, take the square root. When I take the square root on both sides, I must have plus or minus. Now, since I have that plus or minus, I'm going to split it into two different cases. So I have the case where it's plus and I have the case where it's minus, and then I simplify. So the case where it's plus, okay, well, first I solve for a, then the case where it's plus, a equals 5 plus b minus 5, or, don't forget the magical word or, a equals 5 minus the quantity b minus 5. Simplifying each of these, I get a equals b, or a equals negative b plus 10. So in this case, sometimes a equals b, but as I can see on the right, not always. So therefore, this is not going to be one-to-one, and I interpret that and I write out my sentence. It was shown that if f of a, oops, I should have a g in there again. If g of a is equal to g of b, then a does not equal b, therefore g of x is not one-to-one. All right, now thinking about some inverses here. Use the graph of y equals f of x and y equals g of x to evaluate the function. So thinking about what this means, in this case here, g inverse of x, okay? G inverse is going to be the, switching the x and y of g, that's going to give us the inverse. So that means that the x's of g become the y's of g inverse. So the x of g becomes the y of g inverse. And the y of g becomes the x of g inverse. So when we look at the graphs, we're only given the graphs of of f, and we're given the graph of g. So for this first one, we're focusing on the graph of g. So this says, if I'm looking for g inverse of x, what I'm looking for is I have a typo in this. All right, let's do g inverse of 4. So let's change that to g inverse of 4 instead. So make that little x there as a g inverse of 4. Turn that into a 4. Okay, so if I'm looking for g inverse of 4, that 4 is the input of the inverse, but it's the output of g. So that means that the 4 is the y value of g. So if I look on the graph for g and I find the y value of 4, here's my y value of 4 for the g graph, and I'm going to go over and I'm going to find the value here. And it looks like that y value of 4 is going to give me an x value of 2. So this point here on the graph, 2, 4 of g, becomes 4, 2 on g inverse. And so that means that g inverse of 4 is going to equal 2. Okay? So we're using this idea of how the x and the y values switch from the function to the inverse. All right, second one, part B, g of f of negative 4. So here I'm doing my my f function first. So this is going to be g of, let's find f of negative 4. So on the f graph, okay, on the f graph here, I find negative 4, that's my input, and that value gives me positive 4. So now I'm going to look for g of 4, and so over to my g graph, I'm going to find my g of 4. So over on here, looking for g of 4, I find 4, and 4 looks like it gives me 6. And so g of f of negative 4 is equal to 6. Part C, I forgot the number as well. That should be a 3. So on part C, we're going to look for g inverse of f of 3. So G inverse of f of 3. So that means I'm going to do G inverse of, and I find f of 3. So going over to my f graph, looking at my f graph, I find 3. So 3 is about here. Nope, sorry, here. Going down, that looks like it's negative 2. So I'm looking for G inverse of negative 2. And then again, G inverse of negative 2, this value is the input of G inverse, which means it was the output of G. So on the G graph, I'm looking for an output of negative 2. So that's down here. Output of negative 2 looks like it gives me a value of negative 3. And so that means that G inverse of f of 3 is negative 3. Okay. And the last one, part D, we're doing G inverse of negative 2. So G inverse of negative 2, that means I am going to look for, this is the y value of G. So the y value of G of negative 2 on the y value, is going to give me an x value of negative 2. So that's going to be negative 2. So now I want f inverse of negative 2. So f inverse of negative 2, that means that this is the y value of f. So y value of f is negative 2. The y value there of negative 2 looks like it's going to be an x value of positive 1. And so that's going to equal 1. So let me just erase that piece right there. So that means that f inverse of G inverse is of negative 2 is equal to positive 1. If you need to pause the video or go back and re-listen to the explanation to understand those graphs, please do so you really get a good grasp of what the input is versus the output. All right, number 4, use the functions f and g to find G inverse of f inverse of negative 3. Okay, so here we know that we're going to first find f inverse, and then we have to plug into G inverse, and with the value we're going to plug in first is negative 3. So what I'm going to do is I'm going to take my f function and I'm going to first find what is the function for f inverse. So we know we're going to take that f function, we're going to switch the x and the y, and we're going to solve for y, and then we are going to rewrite it as an inverse. So go ahead and do that on your own. You can pause the video. And you should get that f inverse is equal to 8x plus 24. Similarly, we know we're going to have to use the G inverse function. And so since we have to use the G inverse function on the outside, I'm going to just go ahead and take my G and I'm going to find its inverse as well, so I have it ready to go. So here's my G inverse function. And so I'm going to take these two now, and now I'm going to evaluate. So now I'm just going to go ahead and do G inverse of f inverse of negative 3. You can pause the video and take a moment to see if you can do that on your own. And what we should have is this. And you'll see that I didn't bring down my left-hand side, so I want to make sure everybody does that. So it's G inverse of f inverse of negative 3 is equal to 0. All right, in part B, lots of typos on this. Part B, that should be just of x instead of negative 3, because that's the problem that we just did. So just change this to of x. So we're going to do G inverse of f inverse of x. And so we already have our f inverse function from part A. You do not need to redo it. So we take our f inverse function here and then plug it into our G inverse function. And so we just go ahead and do that. And so we get G inverse of f inverse of x equals G inverse of 8x plus 24. And we get the cube root of 8x plus 24. Now with this one, I stopped it here because we can simplify this. So this is the cubed root of 8 times the quantity of x plus 3. So if you can simplify the cube root, you want to. So the cube root of 8 is 2. So it's going to be 2 cube root of the quantity x plus 3. And then, of course, we bring over our left side. And we box our final answer. All right, moving on to number 5. So number 5, at the top, we have for a function y equals f of x, the inverse of f is a function if and only if f is 1 to 1. So the inverse of a function is not only a function, it's only going to happen if and only if it's 1 to 1. Another way to think about that, for a function y equals f of x, the inverse of a function, the inverse f is a function if and only if the graph of f passes the horizontal line test. So remember that 1 to 1 is identified by the horizontal line test and vice versa. Okay, so let's take a look at problem number 5. So problem number 5, we're given this function f of x. So here we have f of x is equal to the x minus 4 quantity squared. We want to restrict the domain so that it's 1 to 1 and has an inverse function. So the inverse must also be a function. Okay, then we're going to find the inverse function, and we're going to say the domain and range of both f and its inverse. So first of all, let's think about what we know about f of x. We know that it's a parabola shifted 4 units to the right. So my graph of f of x, I should be able to visualize this, but I recommend drawing it on your paper. Looks like this. I can clearly see that this is not 1 to 1. If I do the horizontal line test, it crosses twice. And so what I need to do is I need to restrict the domain so that I only have enough of the parabola, as much as you can keep, without it not passing the horizontal line test. So what I'm going to do is I'm going to keep 1/2 from the vertex. It doesn't matter if you keep the right-hand side to the vertex or the left-hand side of the vertex. I usually pick the more positive side, just as a general rule. So now with that, let's go ahead and state the domain of f and the range of f with that restriction. So my vertex here, I know, is at the point 4, 0. So my domain is going to be all real numbers, and my range is going to be, my domain is going to be 4 to infinity, and my range is going to be 0 to infinity. Because we're only keeping the part that's highlighted in green. Okay? And so now what I want to do is I want to find the inverse. I'm finding the inverse so that it is a function. So the cool thing about domain and range is that the domain of the function becomes the range of the inverse, and the range of the function becomes the domain of the inverse. All right, so we already know what the domain and range are for f inverse. So I'm going to go ahead and I'm going to just write that out. Domain of f inverse is going to be this range right here. So it's going to be from 0 to infinity. The range of f inverse is going to be from 4 to infinity. Okay, and now I just need to find the inverse function. So I'm going to go ahead and find the inverse function. You guys can do it. Switch the x and y and solve. So here, I switch my x and y. It's really nice to label your work f inverse. X equals y minus 4 quantity squared. When I take a square root, I need to have plus or minus. With this plus or minus, I then need to decide which one I'm going to keep. Because of what I restricted here for my domain and range, I kept the right-hand side of the parabola. Then I'm going to keep just the positive x, and I get y equals square root of x plus 4. And then I write that as an inverse. F inverse of x is equal to the square root of x plus 4. And we have our domain and range of the inverse here, and we have our domain and range of the function on the left. And last, number 6. Similar idea. I challenge you to pause the video right here and see if you can do this one on your own. It's a little bit more complex, but see if you can try it. All right, so the first thing that I would do is I would visualize what we have. This is why it's so important to understand your parent functions. So visualizing what we have, here's your graph of f of x. Then I need to decide which part I want to cut off, so I'm going to keep the part to the right of the vertex. Again, it doesn't matter. Now I'm going to write the domain and range for this. Here's my domain, and here's my range for the function. Now, because of this domain and range, I already know that the domain and range of my inverse are just going to be switched. So here's the domain and range of my inverse. My domain is now negative infinity to negative 2, and my range, oops, I need a bracket on that, and my range is from 1 to infinity. And then I'm going to actually find my inverse. So I'm going to take my function, I'm going to switch the x and the y, and I'm going to solve for y. So I take my function, switch the x and the y, notice what I wrote on the right-hand side. I wrote the restriction that I'm using. This is for x is less than or equal to -2, right? Because I know that that's the domain that I'm working with here, okay? And then I solve for y. So here I'm solving for y. Now I end up with the absolute value. Remember, when we have absolute value, we need to split it into the positive and the negative. So when you're splitting it, think about this restriction, okay? So the positive, negative x, so we have y minus 1 equals negative x minus 2. So we keep the part inside the absolute value as positive. And we need to think about the restriction. Does this restriction work for this situation? And the answer is yes. Okay, so then I can continue to simplify that one. And when I continue to simplify that one, I end up with y equals negative x minus 1 for x is less than or equal to -2. And that is the restriction that I wanted, because that's what I picked. So that's my inverse. So that means f inverse of x is going to equal negative x minus 1 for x is less than or equal to -2. But let's also think about the other case when we split our absolute value. So this is the positive case. Then we also have to do the opposite. So when I do the opposite, I want to just show you what it looks like. So when I do the opposite here, I end up with y minus 1 equals the opposite of x minus 2 for x. Now, this only works for x is greater than or equal to -2. And this is how I know that I don't want this one, because the domain that I chose was less than or equal to -2. But I could just continue to solve that one just to show you what it looks like. And so I end up with this one. So if I picked the other side to keep, then I would use this equation here. Okay? But I chose the right side after the vertex, so I keep everything that's boxed. All right, make sure you understand this, really think about it, think through how the restrictions make sense, and they validate the problem. That is all for lesson 1.6.